Hello and welcome, dear students. Today we are going to discuss the topic ocean bathymetry mapping and its importance. A fascinating and mysterious underwater world lies beneath the calm oceanic surface that has been mesmerized by human beings for thousands of years. Unveiling oceanic topography has always been an uphill task, but due to the advent of science and technology, marine scientists and explorers are able to explore the ocean bottom topography and biodiversity. This has been possible due to use of bathymetric maps by the marine explorers and scientists. These maps provide a widespread representation of the relief features of the ocean bottom. It is the measure of the depth of water in oceans, seas and lakes. Hence, maps that show depths of water in oceans, seas and lakes are known to as bathymetric maps. Bathymetric maps, well known as a depth chart or seafloor map, depicts the contours and underwater features. Bathymetry is the aquatic equivalent of terrestrial topography, comprising the measurement of the depth of water bodies and the charting of the shape, features and elevation of the submerged landscape. Bathymetric maps, which utilize isobaths to connect points of equal depth, are fundamental tools for visualizing the three-dimensional structure of the seafloor, revealing features such as abyssal plains, mid-oceanic ridges, trenches, seamounts and continental shallows. This science transcends basic cartography. It is a foundational property of marine systems, integral to the studies of physical oceanography, marine geology, geophysics, biology and chemistry. Bathymetric maps utilize a diversity of data sources like sonar, remote sensing, satellite imageries, AI and machine learning to precisely show the shape and the depth of ocean bottom relief features. These maps are more than a practical tool, as they offer a bird's view into an underwater world that is largely out of sight from our eyes, showing a variability of tectonic formations. Underwater mountains, cynons, trenches, mid-oceanic ridges, as well as ecosystems of marine organisms, and provide comprehensive understanding of tectonic processes, geological formation, behavior of ocean circulation, and currents, as well as marine ecology. These maps are highly applicable for scientific research of oceans and lacustrine deposits, navigation, fishing, commercial activities, exploration of oil and natural gas, fishing, biodiversity conservation and hazard mitigation. Now let us discuss history of bathymetric mapping. The quest to understand the seafloor is centuries old, characterized by incremental technological breakthroughs that have progressively unveiled the complexities of the deep. For millennia, depth measurement relied on primitive lead line techniques, lowering a weighted rope or cable from a vessel until it reaches bottom. However, measurements calculated this way were often incomplete and inaccurate because the rope often was shifted by oceanic currents and did not travel straight to the bottom of ocean. The rope could also only measure depths one point at a time. To get a clearer picture of the seafloor, scientists would have had to take thousands of rope measurements. Now let us discuss early methods. The origin of bathymetric mapping extend to early civilizations, including the Egyptians, yet the formalization of systematic hydrographic surveying emerged only within the past 2 centuries. A significant methodological advancement occurred during the mid-19th century. when American and British expeditions initiated systematic mapping of the Atlantic Ocean using the lead line sounding technique. This method involved lowering a weighted rope or hemp line from a drifting vessel until it contacted the seabed with depth inferred from the deployed length. Although lacking in precision, this approach was operationally effective for broad-scale reconnaissance. Refinements to this methodology, notably the replacement of rope with a calibrated steel wire, substantially enhanced the accuracy and reliability of depth sounding. These improved techniques directly facilitated several landmark discoveries in marine geomorphology, including the identification of Mariana Trench in 1875 and the subsequent delineation of Mid-Atlantic Ridge and Challenger Depth in 1877. In 1846, Henry David Thoreau produced one of the earliest known bathymetric maps of the North American lake during his residence at Weldon Pond. Simultaneously, the United States Lake Survey commenced its systematic hydrographic charting of the Great Lake. Now, the modern bathymetric mapping techniques. Contemporary bathymetric mapping has undergone a transformative advancement driven by concurrent innovation in acoustic remote sensing and satellite-derived bathymetry. The integration of high-resolution multi-beam sonar system with advanced processing algorithms now enable the generation of precise three-dimensional digital elevation models of the seafloor, facilitating exploration and analysis at a resolutions previously unattainable. The foundational principle remains active acoustic sounding, wherein a vessel-mounted transducer emits a controlled pulse of sound energy towards the seabed. Depth is derived by measuring the precise two-way travel time of the acoustic signal, applying the known speed of sound in water to calculate range. The critical technological evolution lies in the transition from single beam to systems. Rather than a single downward-looking beam, an MBES transmits a fan-shaped array of hundreds of narrow adjacent acoustic beams across a wide swath but perpendicular to the vessel track. This methodology yields a dramatic increase in data density and spatial accuracy. By simultaneously collecting a dense grid of depth sounding, MBES system resolves not only bathymetry but also seafloor backscatter intensity, which correlates with substrate composition. The resultant data sets provide a comprehensive and detailed representation of seabed morphology, enabling the identification of fine-scale features, quantitative geomorphological analysis, and the creation of realistic shaded visualization. This represents a paradigm shift from one-based depth profiling to true high-resolution mappable seafloor characterization. The evolution of advanced data processing workflows, augmented by machine learning, algorithms, and artificial intelligence, is enabling the more rapid and accurate interpretation of these complex data sets. These integrated capabilities are critical for generating the detailed three-dimensional models required to understand benthic ecosystems, assess geological resources, and information that sustainable management of marine spatial planning. Similarly, modern Lochstein bathymetric surveying synthesizes high-precision echo sounding with a real-time kinematic global positioning system. This integration permits the collection of dense geo-referenced sounding in inland water bodies of any scale. Subsequent data processing within geographic information systems environments facilitates not only the creation of high fidelity bathymetric maps but also enable sophisticated volumetric analysis and the modeling of hypsometric relationships, providing essential data for hydrological studies and water resource management. Now let us see remotely operated vehicles and autonomous underwater vehicles. They serve as a specialized platforms for high-resolution seafloor characterization, particularly in structurally complex or logistically constrained environments. Equipped with multi-beam sonar, side-scan sonar, and high-definition photogrammetric cameras, these systems collect co-registered geophysical and optical data. This integrated sensor suite enables the generation of centimeter-scale bathymetric models, detailed acoustic backscatter mosaics, and photorealistic three-dimensional reconstructions of benthic features. The resulting multi-dimensional geospatial data sets support quantitative analysis of submarine geomorphology, substrate composition, and habitat heterogeneity. Furthermore, these platforms often incorporate auxiliary sensors and sampling systems such as conductivity temperature depths, also called CTD probes, magnetometers, and manipulator arms, allowing for the concurrent collection of water column parameters, geophysical measurements, and physical, geological, or biological samples. Consequently, ROVs and AUVs facilitate targeted hypothesis-driven investigations, provided critical ground truth data that links seafloor morphology with geological processes, ecological community structure, and biogeochemical fluxes. Features of the bathymetric maps. The main features of bathymetric maps that make them such a precious tool for marine investigation and research include contour line. One of the unique features of bathymetric maps is contour line. Contours connect points of equal depth on the oceanic sea and lakes floor that is helpful in understanding shape and structure of the bottom relief features. If contour lines are be closely spaced, it represents steep topography like underwater syenons or ridges, and they are widely spaced that represents areas of gentle slopes. By observing these contour lines, marine scientists and students can easily identify various key underwater features like mountains, ridges, valleys, and trenches. Hypsometric tinting is one of the most element of bathymetric map that provides important information regarding the seafloor and its features. This method uses diverse colors to point to different depths, helping us to easily differentiate between low and unfathomable areas. It can also be used to bring to light areas of research interest, for example, seamounts, underwater volcanoes, etc. Shaded relief is a cartographic technique employed to generate a three-dimensional representation of the seafloor topography. This method synthesizes bathymetric contour data with simulated illumination to produce a map that enhances the precipitation of depth and terrain variation. The resulting visualization offers a more detailed and physiographically realistic depiction of the submarine landscape. This technique facilitates the interpretation of benthic geomorphology, allowing researchers to identify and analyze features such as escarpments, submarine valleys, and syenons with greater clarity. A bathymetric profile is a two-dimensional cross-sectional representation of subaqueous terrains along a defined linear transect, plotting depth against horizontal distance. It provides a quantitative visualization of the submarine topography, translating point or contour-based bathymetric data into a longitudinal section. These profiles are critical analytical tools in marine geoscience, enabling the detailed examination of seafloor geomorphology. They facilitate the precise measurement of morphometric parameters such as the slope gradient, relief, and other features, including seamounts, mid-oceanic ridges, abyssal hills, and submarine synons. Bathymetric maps possess the capacity to characterize the textural properties of seabed substrate through methodological applications of color ramps and shaded relief. These maps can delineate and accentuate regions of distinct sedimentary composition and geophysical character, such as unconsolidated sands, cohesive muds, and consolidated bedrock. The resultant data provides critical insight into the lithology and physical structure of the bathic substrate. This information is foundational for interpreting sedimentary process, erosional and depositional regimes, and broader tectonic history. The fidelity and resolution of bathymetric map are fundamentally determined by underlying geospatial dataset, which is an amalgamation of discrete depth measurements or soundings. These data are acquired through a suite of complementary platform technologies, including satellite altimetry, shipborne single beam and multi-beam sonar systems, and autonomous underwater vehicles. Equipped with high-resolution mapping sensors, each georeferenced sounding constitutes a quantifiable observation of the distance between the sea subsurface and the seabeds at a specific coordinate. The synthesis of these disparate point measurements through statistical and geospatial interpolation techniques generates a continuous gridded model of the seafloor's topography. Importance of mapping of the ocean floor. The ocean floor constitutes a critical geophysical domain for a climate regulation, biogeochemical cycling, and the reconstruction of Earth's geological evolution. High-resolution seafloor mapping is therefore an essential scientific and operational endeavor. It enables the precise delineation of fundamental submarine geomorphological features, including mid-oceanic ridges, subduction trenches, seamount provenances, and tectonic plate boundaries, yielding critical insight into geodynamic processes and the distribution of associated mineral and energy resources. Operationally, these maps support the sustainable management of marine resources by identifying potential fisheries, habitats, and mineral-rich zones, while simultaneously providing the baseline data necessary for environmental impact assessments related to seabed exploration, deep sea mining, and subsea infrastructure development. Furthermore, bathymetric models have become indispensable tools in climate change research, informing projections of sea level rise impacts, modeling changes in thermohaline circulation, and assessing the vulnerability of coastal land benthic ecosystems. And it transforms the opaque seafloor into legible domain of scientific inquiry, resources management, and environmental stewardship. Navigations. Indeed, the generation of precise bathymetric map constitutes a cornerstone of modern ocean exploration and maritime navigation. These cartographic products provide an essential spatial framework translating the submerged topography into a navigable format that enhances safety and operational efficiency across all marine activities. For surface vessel, bathymetric maps delineates safe shipping lanes by indicating shallow areas, submerged ridges, and pinnacles that could pose grounding risks. For submarines, they are indispensable for navigation and maneuverability, providing essential data on water depth, trench locations, and overhead clearance. For military and research submarines, high-resolution bathymetry is vital for safe piloting, terrain related to navigation, and mission planning. These maps are used to survey the select stable hazard-free routes across the seabed, minimizing environmental impact and engineering risk. Oil and gas exploration. Bathymetric maps serve as a critical geoscientific tool within offshore hydrocarbon exploration, providing essential data for prospecting and operational planning. Accurate bathymetric analysis aids in the selection of drilling targets by highlighting features indicative of hydrocarbon traps such as submarine fans, channel systems, and structural highs. Concurrently, it enables a preliminary geohazard assessment by identifying seafloor conditions that may compromise drilling safety or productivity, including steep slope, fluid explosion features, and unstable substrate. Consequently, bathymetric mapping reduces both financial and operational risks by guiding exploration efforts towards viable prospects and away from areas with a higher probability of obtaining non-productive or hazardous. Study of marine ecology. Bathymetric mapping serves as a critical tool for marine ecological research and ecosystem-based management. High-resolution seafloor models provide a fundamental spatial framework for bathymetric habitat characterization, enabling researchers to correlate biological communities with specific geomorphic features. This geospatial correlation is essential for analyzing species distribution, understanding biogeographic pattern, and modeling ecological connectivity across the seascape. Furthermore, these maps are indispensable for assessing ecosystem vulnerability and informing conservation policy. By delineating the physical structure of biologically sensitive areas, including vulnerable marine ecosystems, also called VMEs, and essential fish habitats, EFHs, bathymetric data allows for the quantification of exposure to anthropogenic stressors such as bottom trawling, resource extraction, and infrastructure development. Consequently, the information is integral to marine spatial planning, supporting the design of marine protected areas. Now let us discuss fisheries management. Bathymetric mapping serves as a critical geospatial tool within fisheries science and management. These maps facilitate the identification of essential fish habitat, including biological productive features such as seamounts, submarine cynons, and shell breaks, which function as aggregation sites for key species. This spatially explicit environmental data enables the implementation of specially refined management strategies. Consequently, fisheries managers can employ these maps to inform science-based decisions, such as establishing area-specific catching limits by fishing quotas, thereby optimizing conservation efforts and promoting sustainable harvest in regions of concentrated fish biomass. Now let us discuss climate change. Bathymetric mapping has emerged as a transformative tool in climate change research, providing a dynamic chronicle of our evolving ocean. By creating high-resolution, three-dimensional portraits of the seafloor and monitoring its change over time, scientists unlock critical insights into how rising seas and shifting currents reshape marine ecosystem and threaten coastal populations. This geospatial intelligence unlocks critical insights, allowing researchers to model how changes in ocean circulation redistribute heat and nutrients, impacting everything from global climate patterns to localized marine ecosystems. Furthermore, by establishing a precise baseline of the coastal zones, bathymetric data becomes essential for forecasting vulnerability. It enables the identification of shores at a greatest risk from erosion and communities most threatened by storm surge and sea level rise, moving adaptation planning from reactive to proactive. It empowers policymakers and planners with the evidence needed to design resilient coastal defense, protect vulnerable habitats, and guide sustainable development, ultimately helping society navigate the uncertainties of our changing climate with greater foresight and confidence. Environmental management. Bathymetric mapping serves as a crucial tool in environmental management and marine spatial planning. Detailed bathymetric survey establish a geospatial baseline of seafloor morphology and habitat distribution. Repeated survey facilitate the detection of alterations caused by activities such as dredging, trawling, or the placement of infrastructure, allowing for measurement of erosion, sediment deposition, and habitat loss. Bathymetric data, when integrated with other sensor data, help us characterize seafloor substrate and identify anomalies. This can pinpoint areas of concentrated pollutant deposition, such as accumulations of debris, chemical contaminants, or the extent of plumes from point source discharge, informing targeted remediation efforts prior to approving coastal or offshore developments. Bathymetric maps are essential for conducting environmental impact assessments. They help predict the dispersion of sediments, evaluate the vulnerability of benthic habitats, and design mitigation strategies to minimize ecological damage. By providing the physical template to benthic ecosystem, these maps are fundamental to ecosystem-based management frameworks. They enable managers to delineate protected areas, model the connectivity between habitats, and make informed decisions that balance resource use with the conservation of benthic habitat integrity. Scientific research. Bathymetric maps provide an essential geomorphic framework for interdisciplinary research. These maps underpin empirical investigations across diverse fields, from marine geology and geophysics to benthic ecology and physical oceanography. The detailed characterization of seabed topography, including depth, slope, aspect, and rugosity, provides critical covariates for modeling geological and ecological processes. For example, bathymetric data is indispensable for studying tectonic processes at plate boundaries, reconstructing past sedimentary environments, modeling species-habitat relationship, and understanding hydrodynamic flow patterns that structure benthic and pelagic ecosystems. It transforms the seafloor from an undifferentiated plain into a quantifiable landscape to interconnected features. Accurate bathymetry allows scientists to optimize sampling transects, target specific physiographic features, and select appropriate technologies for data collection. Military applications are another prospects. Bathymetric mapping serves as an essential geophysical intelligence asset within naval and strategic military operations. It provides the fundamental geophysical layers for a range of tactical and strategic applications. Planning, security, and undersea domain awareness. Bathymetric maps are indispensable for special operation. They allow for the precise identification of viable landing zones by analyzing beach gradients, subsurface obstacle, and approaches. This data is integrated with tidal and surf models to minimize risk to personnel and equipment during littoral insertions. In conclusion, bathymetric maps transcended their primary function as technical hydrographic documents. They serve as fundamental spatial frameworks that unlock systematic inquiry into the largely unexplored deep sea realm. By rendering the seafloor's complexity legible, these maps function as critical tools for scientific discovery, enabling hypothesis-driven exploration of benthic ecosystems and subsea geodynamics. Furthermore, they provide the essential geospatial intelligence required for evidence-based ocean stewardship, informing policies aimed at preserving biodiversity and managing anthropogenic impacts. Thus, bathymetry constitutes a vital interface between empirical measurement and the expanded human understanding of the ocean. This was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.